Alrighty guys, welcome to section 4.1. We actually made it out of chapter 3. And I'm going to hope that my voice makes it through this video. It may end up getting split in two, but we're going to aim for one. Section 4.1 is on maxima and minima. I had a little bit of a hard time finding exactly what I wanted for videos online. I put up something about critical points, I think, or stationary points, which kind of leads us into this, but it's not exactly what I was looking for, so I really wanted to do a video for us. We start out with absolute maximum and minimum. Let f to be defined on a set D containing C if f of C is greater than or equal to x for every x in D, then f of C is the absolute maximum value of f in D. And if f of C is less than or equal to f of x for every x in D, then f of C is an absolute minimum value of f in D. An absolute extreme value is also either an absolute maximum or absolute minimum. Sometimes you'll see them as absolute extrema, written like this, when we're talking about both of them. This kind of makes sense if we consider something with an absolute max, right? And you have an absolute max right here, and let's say this is right here is f of C, or not, f of C, then for any other x that I have in here, any x, then f of C is going to be bigger than all of the other f of x values, and we're talking about the same when we look at an absolute minimum. So the minimum, my f of C value here, my y value is less than every other x that's there. Keep in mind this is defined on a set D, so I can set my domain and define where I want to be looking for my absolute minimum and maximum, or absolute extrema. Alrighty, so if we take a look at this picture, if we think about absolute extrema, kind of like hiking a path, and the distance is in the x direction where we're walking, and the y values are the elevation, then all this picture is really trying to tell us is that we have low points here, and what they've done is they've taken this elevation up here and moved it down here to a graph. So we have low points that happen maybe about here and about here, and we have high points, little peaks here and here, right? And so it's just showing that the absolute extrema are dependent on the function and the interval of interest. So if I want to look for my whole hike, I'm going to be looking on my entire hike distance, let's say here, then this may be my absolute maximum. If I'm looking on just maybe the first 10 minutes of my hike and just looking on this interval right here, then this is going to be my absolute max. Okay. So all it's saying is that we need to be aware of the fact that it's dependent not only on the function but also on our interval. So if we take a look at figure 4.2, we have y equal to 4 minus x squared, and we're going to think about that on all reals. So from negative infinity to infinity, then we can see that the absolute value, the absolute maximum of this function is 4 at x equals 0. It makes sense from what we know of parabolas, right? And then there is no absolute minimum for this function. If we look a little bit differently at the same function, but we change the interval, so here we're looking at the same function, but we're looking from 0 to 2 inclusive, then now we have an absolute max at 0 of 4, and we have an absolute min of 0 at x equals 2. So we have both an absolute maximum and an absolute minimum. If we look at the next figure, what we're looking at is now on the interval, this is really all we've changed, the interval 0 to 2, not including 0. So here, because 0 is not included, we have no absolute max, and you probably remember this from algebra. We do have an absolute minimum of 0, again, at x equals 2, so we have only an absolute minimum here. And then the last one, probably not surprisingly, they changed the interval to be 0 to 2, not inclusive of 0 or 2. And in this particular case, there's no absolute max or absolute minimum, right? Because we're not including the endpoints. So keep that in mind, all right? So if we want to look, if we define on a closed interval on the previous ones, when we defined on a closed interval or even a partially closed interval, it guaranteed that we had an absolute max or min here on the entirely closed interval, right? Oh, that wasn't supposed to be like that. There we go. On the entirely closed interval from 0 to 2 inclusive, we had an absolute max or min. The next thing we want to talk about is that's not guaranteed. Sometimes we don't have an absolute max or min, even when we are on a closed interval. So here, if we look at this function, y equals x, if x is between greater than or equal to 0 and less than 1, and x equals 1 or 0 when, let's try that again, y equals 0 when x equals 1. So we end up with a graph like this one right here. So what we're seeing here is there's two absolute minimums here. There's an absolute minimum of 0 at both 0 and x equal to 1, right? Because those are the 2 points here in pink. And then there's no absolute maximum. Because if you look at the piecewise function, when I get to 1, that 1 value is not included. And my x goes back, or my y goes back to being 0 when x equals 1. Alrighty. So here we have a similar situation in B, where it's just showing that if I have a y equals f of x on some AB, and this is an AB inclusive, then I have an absolute minimum of f of a at x equals a. But there's no absolute max here. Because if I look here, there are points here in this area, right around here, where it's greater than what this endpoint is, right? And so there are definitely points on this interval that are larger than the pink point here at the end, but because I'm not including this little maximum area here, there's no absolute maximum. Alrighty. So both of those are examples. This one we were looking on 0 to 1 inclusive, and here we're just looking on A to B inclusive. You can see that there's closed intervals, but we don't have either an absolute, well, in both places, I guess, an absolute maximum, but by the same idea, we could not have an absolute minimum. Alrighty. If we look at the next theorem, the extreme value theorem, it states that a function that is continuous on a closed interval AB has an absolute maximum value and an absolute minimum value on that interval. So what we saw in the previous example was these functions weren't continuous, right? What we saw in the example before that, as we played with the intervals, was that so long as it was continuous and it was closed, then we had the absolute maximum and minimum. So if you look at the extreme value theorem, there's two conditions. For the existence of absolute extrema. And the first one is going to be that f of x is continuous on the interval. So I don't care if it's continuous everywhere, but it has to be continuous on the interval that we're looking at. And then 2, the interval must be closed and bounded. So it needs to have the endpoints included. It needs to have bounds, right? So let's take a look at a couple more examples, and let's see what we can get out of this idea. So if we look at figure 4.4a, then here, if we're looking at this one, we meet our first thing, f of x is continuous. And we can also say that we're looking at f of x on a closed interval AB is closed, right? So by the extreme value theorem, there must be an absolute maximum here, and there must be an absolute minimum here. Okay, so according to IVT, the intermediate value theorem, absolute max and absolute min exist. Oops, min exist. So if I take a look at this particular one, what I see is my absolute max is right here. So I have an absolute max of f of a at x equals a. And then I have an absolute min right here, right? So I have an absolute min of f of c at x equals c. All right? So the extreme value theorem, sorry, I didn't mean to write intermediate value theorem there. The extreme value theorem, what it's telling us is that we definitely are going to see, it guarantees that there's an absolute max and an absolute min, okay? It doesn't mean that there's not an absolute max or an absolute min when the extreme value theorem doesn't apply. The extreme value theorem works one direction only. If I'm bounded and I'm continuous, then there will be an absolute max and an absolute min. So let's take a look at the second example over here. Here